Welcome back to the School Science Shed. This is episode 4 in a series of videos which are aiming to help you revise for GCSE physics if you're studying in England. Physics is the same the world over, so if you're not in England, the information should be useful to you, but you need to check your curriculum to make sure what I'm covering is something that you need to know. And even if you are in England, please don't rely on only these videos for your revision. Check your syllabus and make sure you are covering everything that you need to know. Today we're going to look at reducing wasted energy. So let's make a start on looking at that. One of the really fascinating things about energy is that if you think about all the devices we use today, what they are doing is they are transferring energy from one form to another, and as they do so, they are doing something useful in the process. And we'll look at some examples of that in a moment, but whatever appliance you think of, you will see that it transfers energy from one form to another as it does the useful thing. So here are some examples of things that convert or transfer energy from one form to another. So we've got a car, and what a car does, you put fuel in the fuel tank, and that goes to the engine, and the engine transfers the chemical energy in the fuel into kinetic energy to make the car go. This is a ski lift. So basically what the ski lift does is if you're skiing, it takes you to the top of the mountain, so you don't have to walk up to the top of the mountain and then you can ski down. What it's doing is it's transferring electrical energy into gravitational potential energy because it's making you high up. And this little device here is transferring electrical energy into thermal energy and light. And whereas the electrical energy come from for these two devices, well, it will have been generated in a power station, and this is a thermal power station. It's a fossil fuel power station, so it has transferred chemical energy into electrical energy. So energy converters transfer energy from one form to another, and in the process they do something useful. Now, why are we so keen on looking at energy transfers and preventing wasted energy? Well, in an energy transfer, not all of the energy ends up in a useful form. So in a car, we start off with chemical energy, and that's transferred to kinetic energy. But some of this chemical energy doesn't end up as kinetic energy. It ends up as sound or thermal. And this diagram is quite a useful way of summarising that. We have the energy going in, we've got the useful energy coming out, and then energy that's not useful we have going up vertically, or sometimes you see a diagram where they go down instead, but they're being deflected from the kinetic energy. So that's what happens in a car. Chemical energy is transferred into sound energy, thermal energy, which are wasted, and it's also transferred into kinetic energy. And a similar sort of thing happens in the ski lift as well. Electrical energy is transferred into gravitational potential energy, but some of it will be wasted as sound and some of it will be wasted as thermal. And with the light, I've really spoken about this already. A light, what you want is that to give out lots of light, but when the energy is transferred, some of it ends up as thermal energy instead of light, so that's the wasted form. And in a power station as well, we want the chemical energy to end up as electrical energy, but quite a lot of energy in a power station ends up as thermal energy, which is not the form that we wanted. It's not a useful form. So what we've seen here is that when we've got something that's transferring energy from one form to another, almost inevitably some of that energy is going to end up in a form that we didn't want. It's going to be wasted. If you think back to episode 2, you'll remember that you learned that energy can't be created or destroyed. All you can do is transfer it from one form to another. So you might be thinking, Well, why is this a problem? Why are we worried? Why are we talking about reducing wasted energy? Because if it can't be created or destroyed, it's never going to run out. So everything will be okay. We shouldn't worry about this at all. But there is a problem. So we've already seen, haven't we, that when energy is transferred, some of it ends up in forms that are not useful. But it's worse than that. At the end of the process, energy usually ends up as thermal energy. That's the most common wasted form of energy. And even if there are other wasted forms of energy, they probably end up in the end as thermal energy as well. And the thing about thermal energy is that it tends to transfer from high temperatures to low temperatures. So what we end up with is thermal energy at a low temperature. And thermal energy at a low temperature is not useful. And the word we use to describe what's happened is we say that that energy has been dissipated. It's spread out. It's at a low temperature. It can't be used. It's been dissipated. We saw some diagrams. Let's go back just to have a look at them because I think that would be helpful. And what we will do is we will have a look at the power station. Here we go. Here's the power station which is generating electrical energy. We've got a diagram here which clearly shows we've got useful chemical energy there. We've got energy, chemical energy there going in. We've got useful electrical energy coming out, and some of it's being wasted as thermal. But how much of the chemical energy ends up as electrical and how much ends up as thermal? Well, a way we can show that is by what's called a Sankey diagram. So the Sankey diagram is similar to the diagram we've just looked at, but the difference is we're using the thickness of the arrows to represent the amounts of energy. And what you can see here is that actually in this power station, it's not a very good power station because not much of the energy is ending up as electrical because that's really thin. Most of it is ending up as thermal because that's really thick. And if you get a ruler out and measure on your screen of your phone or your tablet or your computer, if you measure this and you measure that and you add the two together, you should end up with that distance there. Because remember what the conservation of energy says, it says energy can't be created or destroyed. So this chemical energy has to either end up as thermal energy or end up as electrical, and we won't get any extra energy just appearing from nowhere. So they might ask you to draw a Sankey diagram in your GCSE exam. They might ask you a question like this. So we've got an LED, it's transferring 10 joules of electrical energy, 4 joules of it is ending up as light, 6 joules as thermal energy. What does the Sankey diagram look like for that? Well, here's how you do it. First job is to decide on a scale. And I reckon that using 1 centimetre for 1 joule in this particular instance is a sensible scale. So you would start your arrow off being 10 centimetres thick. We've got 4 joules of light, so we want 4 centimetres there, and we've got 6 joules of thermal, so we want 6 centimetres there. That is our Sankey diagram for our LED light bulb. One of the things we're interested in energy transfer is how much of it ends up as useful energy. I think that's been pretty clear from what we've said already. So how do we calculate that? Well, we calculate it by using this formula here. Efficiency is useful energy out divided by the total energy in. So useful energy out by the and we normally like to have it as a percentage. So to get it as a percentage, we multiply by 100. And then, as I said before, there's a triangle because it's got 3 things in it: efficiency, useful energy out, total energy in. There is a triangle which will tell you how to calculate it. If you want to know how to use a triangle like this, take a look at episode 3b where I explain how triangles like this work. So let's have a look. Let's see if we can do this calculation. So it's the same LED bulb we were talking about when we drew the Sankey diagram. What's its efficiency? Well, let's do a summary. We're told energy in is 10. energy out is 4 and the efficiency is what we need to find. Do we know an equation with energy in, energy out and efficiency? Yes, we do. There it is. Efficiency is the useful energy out divided by the total energy in times 100. Let's put the numbers in. So there's the equation. Let's put the numbers in. Useful energy out is 4. Total energy is 10. 4 divided by 10 times 100 gives us 40%. So what we would like to do so that the energy doesn't get dissipated is we would like to make things as efficient as possible. So how can we make a car as efficient as possible? Well, one thing we can do is we can use lubrication. We have oil in the car which reduces friction. That means less energy will be transferred as thermal energy and more will end up as kinetic energy. We can also design the car very carefully. That would be everything about the car, how streamlined it is, how well the mechanisms within the car work. And the other thing we can do is we can control the engine with computers. So if the computer controls exactly how much fuel is going into the engine, exactly when it's set fire to transfer the energy, that can make the car more efficient as well. But in spite of this, cars are not very efficient. And the best efficiency we've got for a car so far is 38%. So in a car, most of the energy that you've paid for from your petrol or your diesel ends up heating the environment. It doesn't end up making your car go forward. Light bulbs, the efficiency, really, what we need to do is we need to choose the right light bulb. So an incandescent bulb has got a thin wire in that's heated up till it's white hot, and then it glows, and that's how it produces the light. Not very efficient. Here's a picture showing an incandescent light bulb. There's that thin piece of wire. It gets really hot. It gets white hot. Once it's white hot, it gives out light, and that's how it provides its illumination. But it's only 2% efficient. For every 100 joules that are applied, only 2 joules end up as light, the rest ends up as thermal energy. A fluorescent light works in a different way and it's more efficient. So in a fluorescent light, you've got a low pressure gas including some mercury vapour. Means you've got to be very careful. You probably know mercury is poisonous. You've got to be very careful about how you dispose of these because they contain mercury. So they've got mercury vapour inside. When the electricity passes through the mercury vapour gives out ultraviolet lights, and then there's a coating on the inside of the glass. This white colour here is a coating on the inside of the glass that absorbs the ultraviolet light and emits visible light instead. It fluoresces, and that's why it's called a fluorescent light. And if we go back to the data about efficiency, look, a fluorescent light is 30% efficient. It's much better than an incandescent lamp. But an LED, which uses electronics to produce the light, that is even more efficient. That's even better. What about power stations? Because we generate a lot of electricity. So how do we make a power station as efficient as possible? Well, it's very similar to a car. We can use lubrication for the moving parts to reduce friction. We can design the furnace and the boiler and the turbines. If you're not sure what those mean, don't worry, because we're going to cover how power stations work in another video. But if you design those very carefully, you can make the efficiency better. And the higher the temperature you use, the better you are going to make things. And we can get powers of, we can get efficiencies rather, for power stations up to about 35%. And there's a type of power station called a gas turbine generator, which can actually get the efficiency up to 60%. But we're still talking, aren't we, about lots of energy being wasted. Another way of addressing that in power stations is to use the heat that's produced for something useful. So this is what's called a combined heat and power station. It's in Denmark. and it burns straw to generate electricity, and then the wasted heat that's generated from that process is used to heat greenhouses. So what you're saying is we've got some energy here, it's being wasted, we might as well use it for something useful. It's called combined heat and power because it produces power, electricity, and it produces heat which is used for something. What about your central heating at home? Well, in your central heating at home, it burns methane, so that's combining it with oxygen, and that produces carbon dioxide and water. And if you've got a really efficient boiler, it will take a lot of the energy out of the waste gases. These waste gases will be really hot because the energy that's been transferred to thermal energy. If you can take a lot of energy out of those gases and use it to heat your water in your central heating system, the water in the radiators, then it's going to make it more efficient. And it would be particularly good for reasons which will become apparent later on when we study about the particle theory. It'd be really good if we could turn the water as a gas, water vapour, into a liquid. That would make it even more efficient. And the type of boiler that does that, because it's condensing water from water vapour into liquid water, is called a condensing boiler. That's really efficient. Once you've heated your house, what you want to do to reduce energy loss is to keep the heat in your house for as long as you can. You're onto a losing battle because heat will move from thermal energy will move from an area where the temperature's high to an area where the temperature's low. And you've got your central heating on because it's cold outside. And you don't want it to be cold in your house. So you put your central heating on to heat the house. So the house is hot, outside's cold, heat is eventually going to escape from your house to the outside. How can we slow it down? Well, there's various things we can do, and they're all on that. They're all on that slide there. I will talk about draft excluders because they're the simplest. The idea of draft excluders is you stop warm air escaping from your house and you stop cold air coming in. What about the other three? Well, cavity wall insulation first. If you go back before 1920, houses used to have a single wall on the outside. It might be more than one brick thick, but it would be one wall. And the bricks that were used were really expensive because they had to be strong enough to support the house and they had to stop water getting in. And then in the 1920s, people realised, well, we could get away with using cheaper bricks if we had a gap between the two walls. We could do two things there. We could use some really cheap bricks for the inside layer, because if they look horrible, it doesn't matter. We're going to put plaster on the inside and nobody's going to see this bit here. And then on the outside, we need some bricks that are going to look nice, but they don't need to be really good bricks. They can allow water to penetrate, because once the water's soaked into the bricks, they're not going to get to the second layer because there's a gap. And that is called a wall cavity. And then a bit later on, when people started to get very worried about energy escaping from houses, it then occurred to people, well, actually, if we put an insulating material in between the two layers, and if it was a material that didn't allow water to get through, it would actually mean that less heat passed through the walls. So that's what cavity wall insulation is. It's insulation in the gap between the two walls of a house. There's also space in your loft. So your loft is above the ceiling of your bedroom in the roof space. And there'll be some supporting planks of wood going across the loft. And if you fill the gaps in there with insulator, that will reduce the amount or reduce the speed at which heat leaves your house through the roof. And then something else you could do is double glazing. Glass is not a particularly good conductor of heat, but it's not a really good insulator either. And if you feel, even double glazing, if you feel your double glazing, you will feel that it's colder than the walls of your house. And the reason for that is heat is going through the glass quicker. But you can make it a much better insulator by including some air, or normally actually they use argon gas in a gap in between two panes of glass. So you have a pane of glass there, you've got argon gas in the middle, and then another pane of glass. And as long as you don't make this too thick, the argon gas won't start to move around. If it starts to move around, it'll actually transfer heat a little bit better. But if you keep the gas fairly narrow, then the argon inside can't move around, and trapped air is always a good insulator. And if you're thinking, as you would have to if you were designing a house, how much heat is being transferred out of the house, well, the speed with which energy is transferred through a material depends on, first of all, the area of the material. So if you think about a window, the bigger the window, the faster energy is going to pass through it. The thickness of the material, the thicker the material, the less heat is transferred. The temperature difference between the inside and the outside. And then finally the material itself. Materials have a property called thermal conductivity, and the higher the thermal conductivity, the faster thermal energy will be transferred through that material. So that takes us to the end of episode 4. I hope it was useful for your revision, and if it was, please give it a thumbs up. Makes it easier for other people to find the videos if they're useful. If you've got any questions, put them in the comments. I've really enjoyed explaining this section of physics to you. Looking forward to episode 5, but until then, good luck with your revision.